Hello, my name is Wesley. I'm a student at the School of Geoscience at the University of Witwatersrand in South Africa. My research project is focused on studying the feasibility and use of the resistivity method within a mining context around the eastern Bushveld Complex region. Now, resistivity is a physical property of all material and is used by the DC resistivity method to map the subsurface geology. Unfortunately, very little resistivity studies have been conducted within the eastern Bushveld region. The Bushveld Complex itself is one of the largest layered intrusions on the planet and contains the highest percentage of platinum group elements in the world. My study area is placed in the northern parts of the eastern Bushveld Complex at Anglo Americans in the Beecroft Platinum Mine. I make use of three different resistivity methods. The first method, I use a sample core IP tester to measure individual resistivities of core samples that have been brought out by the deepest exploration boreholes. I then plotted these resistivity measurements in accordance with the depths, and I found a relatively high resistive layer at 22 meters depth of the northern side, surrounded by a less resistive gabbronorite. Now, this higher resistive layer can be used as a targeting horizon for exploration, since the Marinsky Reef is around 100 meters below this layer itself. The second method I use is 2D resistivity profiling, where I constructed the resistivity profiles near exploration walls once again, using the automatic resistivity unit, also known as ARES. I then use three different processing methods to test their feasibility within exploration. The first two profiles you see here are field processed and bad data point removed processed. Now, these are the most general forms of the resistivity profiles we find in exploration. The third profile, however, has been carefully processed and analyzed in accordance with the surrounding geological environment. The first two profiles themselves show resistivity contour at 12 meters depth of around 1,700 ohms per meter. This is contradiction of the actual SCR heat test, which showed that at 12 meters the resistivity is around 1,220 ohms per meter. But when we look at the carefully processed profile, the resistivity layer at 12 meters is 1,200 ohms per meter, which does correlate with the SCR heat test themselves. We also found that for some profiles we can reduce the root mean square error up to around 20%. This means that the resistivity contours themselves will be moved to the correct depths and in turn correct the geological model produced by the resistivity profiles. This shows again the importance of correctly processing resistivity data. These 2D profiles seen here detected subsurface boulders within the region. Now, these boulders play a huge role in hazard assessment for continuous mining, and 2D resistivity methods provide a cheap and efficient way to detect these boulders. We also create a synthetic three-dimensional model in order to test the feasibility of detecting these boulders with three-dimensional resistivity, and the results show that it's actually even more efficient to use three-dimensional resistivity due to the high resolution of the technique itself. Our last two figures there, 2 and 3-dimensional resistivity profiles were constructed over dike swarms detected by aeromagnetic methods. Now, these aeromagnetic methods predicted the width of these dikes to be around 100 meters, but the high resolution ground surveys of the resistivity methods reduced this width to around 60 meters. Now, this again will be used in hazard assessment within the mining context. So, in conclusion, the resistivity method managed to find a highly resistive layer at 22 meters depth, which could be used in exploration for the Marinsky Reef, as well as hazard assessment methods to either detect subsurface boulders or dike swarms themselves. But this can all only be done if the data is correctly processed. Thank you for your time.